AI plays multiple roles within EDA. The application of AI into design tools and flows will take several forms, each independent but all potential working together. AI's infusion into our world may seem sudden and unexpected, but the EDA has been quietly adopting it for more than a decade. What changes is that it's now becoming more visible thanks to increasingly powerful large language models (LLMs) and the need to apply them to increasingly challenging multi-physics problems. Two fundamental shifts underlie AI increasing prominence. First, heat is becoming a barrier for large package sizes and higher integration levels. As a result, power, thermal, and mechanical are now bound tightly to the physical aspect of the materials used for construction. Second, the shift left. The desire to have better information available earlier in the flow in order to make more informed decisions. It's being coupled with top-down design practices. Both of these changes bring the influence of physical into architectural decision involving flow planning and partitioning and integration choices for 2.5D and 3D assemblies. This is where AI can help, and it does so from two directions. One inside of the EDA tools, making these tools more capable and versatile. The other is outside of tools, providing useful data to engineers. While they can be coexist, these approaches use different forms of AI. In addition, AI can be used to help link up all of this together by building suitable executable designs and verification models to use an abstract of the physical devices. Those use cases may contribute to enhanced methodologies enabling better designs more productively. At listeners, when discussing AI within the context of EDM, the term model becomes confusing, and that is used for different things. The first one is the AI model, such as a large language model. It is used by an inference engine to provide an answer based on a trained model. The second is the EDA model, which could be part of the design or verification (DV) framework. This uses an execution engine that responds to the stimulus and may or may not utilize AI. It can become especially confusing when an AI model is used to create an abstraction of an EDA model. Attempts have been made to clarify this as much as possible. Inside or outside, there are several factors that influence where AI is utilized. It could be used to replace or enhance an existing algorithm with the tool, or it could be more agentic and used to drive the tools as if it were an engineer. One of the advantages of AI being outside is we can tool agnostic, says Amit Gupta, Vice President of the General Manager of the Siemens EDA Customized Division. Then the AI can core internally created tools or third-party tools. The AI player is doing intelligent calling of tools and integration with the tools. So why do we put AI inside the tools? The advantage we get when we couple them at the server level is there are often a lot more knowledge and information they can train the AI with. You can get a performance improvement as a result of that. Others agree. We think of AI as a companion to our tools and as a way to augment as opposed to replace or substitute, said Ananda Trivinagandam, Product Management Senior Director at Synopsys. We do not see tools being out of the loop. Tools will always be in the loop, especially for sign-off. We see the need for the tools being there as a guardrail. You can have AI do a lot of front-end stuff. You can have AI do a lot of prediction, optimization, and etc. But ultimately, you will always need a tool and the loop to sign off. Agentic AI takes this in a different direction. The nice things about agentic AI as a concept is that you can consider it to be humans, just artificial, said Michael Swinsky, chief marketing officer and artist. You basically give it a higher degree of freedom to do specific tasks and then they orchestrate those tasks to work in unison based on different levels of trade-offs. How much freedom you want to give it is where we, the human in the loop, is still gonna remain part of the process. You don't have a department of engineers where you can ask one to focus on performance and another to focus on area, or focus on the throughput or focus on over schedule. You basically have the little team. It just happens to be agent versus the human agent, and they all have some domains expertise. Rapid progress is being made on this front. There is a lot of there is a lot of tool iteration that needs to happen, says the Vamsi Balanga, co-founder of CTO of Particle. For example, tool settings and updating RTL based on a test bench or PPA results that are best done via an agent that codes the tools akin to how a human behaves today. For now, the agent aren't great at this, but they will get better, particularly as tools are modified to enhance their reasoning abilities that can make it easier to build reasoning abilities that can make it easier to build flow that are usable by a large number of engineers. It has a huge value at the front end, and we might want to go through from specification to RTL or system C, or looking at the specification of the previous generation, design gonna next generation design. So the Group Director of Strategy and New Ventures in Cadence. How could I create a deliberate product to satisfy this new market? This is rich and important industry where LLM-based AI, generative AI, agentic AI has tremendous opportunity to show value. There is a swimming pool that is natively good at, and something that has a huge amount of value. Integrating AI inside the tools also can provide a lot of value in some cases. Historically, we are using AI externally for an application, such as Gupta. Then we did some benchmarking to find the advantage that we could get by coupling AI with the server itself. We were able to get a 2x or 30x performance advantage by coupling it with the server and having more information coming from the server directly to the AI, which would have been available otherwise through the AI API. The internal augmentation is often based on the problem that you are trying to solve. The deeper the connection to the physical processes, the more tightly integrated with the neural network needs to be within the tool. Said Parker's Balanga. Since physical design tools are solving these three difficult 3D optimization problems, make sense to integrate our trained models deeply into optimizers to help us find a better solution. The need for abstraction. New models require to shift left. This needed to have the right amount of details in execution performance. We can certainly handle these physics and multi-physics problems at the transistor level, said Gupta. The industry has been doing for a long time. It started with the process design kit, PDKs, These give you information about how transistors are getting to perform, such as the IV curves. Then we use machine learning and reinforcement learning to build numerical models from that data to do prediction and handle those multiple physics problems. Those abstractions are beginning to influence many aspects of the flow. When it comes to optimization, decision making is critical, and some sort of model is typically used, said Benjamin Crouch, group manager for advanced mixed signal automation in the Fraunhofer IIS engineering of adaptive system division. For instance, there is work on new optimization approaches that bypass extensive simulation involving 3D EM servers. They use a network trained by a reasonable amount of initial and expensive simulation runs. Optimization is then significantly accelerated by using those trained design models, thus yielding a better overall result. However, it must be stressed that investment in the initial simulations and training should have a promising ratio with respect to the saving. Over the past couple of years, LLMs have stolen the show. Directly applying LLMs won't get you very far, said Balang Naga. Language models are not well suited to handle detailed physical information that needs to be encoded into specialized AI models. Using AI for problems close to the physics requires careful handling, as well as injecting some domain knowledge into model design and training. EDA-specific domain models are still evolving. The models are fairly capable today, and there is a lot of advancement happening when it comes to foundation models and the knowledge that they possess. So the synopsis is Tiruvengadam. The foundation models have certain capabilities, and there is a way to customize these foundation models. That is where, in context of EDA, they have to customize the LLMs for their particular domain or context. And that's how you improve the accuracy of the response for that particular domain. That is not as easy as it may sound. When people talk about the physics AI, they are talking about it from a generative and agentic perspective, said Gupta. Historically started with a large language model that understood language very well. Now there are large investments going into broadening data from language models to physics models and being able to handle other domains besides the language. They're having a success. Multi-physics means problems that span multiple physics domains, and LLMs aren't well equipped to handle this today, said Arvind Srinivasan, product engineering lead at Normal Computing. Historically, we solved these problems with simulation. Now people are trying to embed physics into AI training. AlphaFold is the gold standard. It combines reinforcement learning, physics constraint, and simulation. That worked because you could quickly reject invalid protein faults. In hardware, running a full simulation takes hours. You don't get that quick reward signal. That's a big problem. What are the relevant design and verification models that the EDA can use? AI is enabling a link between the language and a mathematical structure, set up from Fraunhofer Proust. This could be a constraint graph, which is commonly found within EDA. AI will probably act as converter from a requirement into structure, or preliminary part of the constraint of it, and vice versa for verification. As existing algorithms need to become more aware of multi-physics issues, there is an opportunity to assess the benefit of the AI assistance. Placement-aware gate resizing is a problem very close to physics, but also exactly the type of problem the neural network have shown promise at solving, said Balanaga. This model is doing the equivalent of heuristics that have been hand-tuned in existing tools over decades. Our philosophy mirrors the approach of AlphaGo, which surfaced hand-tuned expert systems by discovering better decision processes. The solution is a combination of synthetic data and reinforcement learning. AI generated models. A cornerstone of semiconductor design uses an abstraction of transistor to provide gate-level models. These models have adequate accuracy with much higher simulation speeds. Shift left requires abstraction that enable informed decision-making at all stages of the development flow, and that requires a plethora of new models, but models are expensive and create and validate. That has many people looking at AI to create necessary models, which either could be executed by traditional engines and inferred like an AI models. Analog verification needs fast, but accurate models. Verification will be supported by accelerated generation of the surrogate models as required for system simulation. Side approaches. This is important to enable system-level models, and especially for AMS, whether the tedious simulation can be replaced by an AI surrogated model. EDA always has used data-driven methods such as simulation and annealing. The real difference with generative AI is that you can use past simulations as training data for very large models to improve the downstream simulations, or tell the LLMs to translate huge specs into physical constraints, said Nomer Srinivasan. But if the validating AI-generated RTL or test plans takes just as long, building them yourself, you haven't saved any time. AI won't replace areas where reviewing the material that is generated does actually reduce the workload. The technique is getting around. You can take a design and train a model on that design. Said Rich Goldman, Director of Electronics and Semiconductor PhD Unit Analysis, not part of synopsis. The unit tons of data, thousands of data points that form part of a sweep. You take your design, you challenge it a little bit, and run that to get the results. And then the changes a little more, one more parameters, a little bit, and you sweep through. That is your training data set. Once you train an AI models and that take a long time, you apply it to your design and you get back a result almost instantly. All this learns and take weeks and months. You can get instantly. You can apply that to many different designs and many different iterations and get the best design. That is not going to get you 100% accurate result. It will get you 90% to the 95%. Small language models, SLMs, can help there because they can target it at specific problems, which reduces cost and the complex scale of the models. But scaling down from FP32 to FP16 and below also raises some questions about the accuracy of result. You want to distill knowledge from bigger models and injection that into small models, but also be able to prune the weights, said William Wang, CEO of Chip Agent. So instead of using a 16 bits, you may 8 bits to store the weights. Everything is compressed. There are also these well-known algorithms to compress the weights and make it smaller. You also need to get a certain level of accuracy. This is made worse by data scarcity in the EDA. One of the most significant issues associated with AI is obtaining enough training data to get the quality of LLMs to the point where they can be reliable, said Dave Karpf, CEO of Record Verification System. We are now seeing the application of SLMs and other techniques to get around the sparse data issue, and it will be the thinking that drives practically an AI application. Combining AI expertise with EDA experiences seems critical to optimize the use of these new technologies. Reinforcement learning can start with a smaller data set. In order to do reinforcement learning, you need two things, said Balanaga. For the replacement of where gates reside in problems, you need a model that making a prediction. For example, a better set of gate size and environment such as time analysis engine that learns very quickly. And training happens in this loop with the model exploring a bunch of different gate sizes of a large number of synthetic netlist. Immediately, this is less efficient than having a large number of netlists with optimized gate sizing. But without the data existing, we have to spend compute to generate the data. This can affect accuracy. As we go up, additional layers of abstraction, and where natural language becomes the next level of abstraction, having a firm ground in the underlying computation is incredibly important, said Cadence North. You can't go to another layer of abstraction without having a path and accuracy of what is actually happening underneath you. Otherwise, that abstraction loses accuracy. You become less effective, and the end result is not as compelling as it could be. Questions about accuracy are typically with the AI models. People are confused between the estimation and correlation, said Arthur Swinsky. It would be great to have things that are fully correlated, but many things change the workload. You can something at the system level. How it's gonna be a one-to-one mapping to how you implement that. We've built a notion of physical awareness. And the architectural level trade-offs will be basically clean enough about placement, congestion, blockage, front place routing, and wire length calculations, while understanding the impact of power. Typically, front-end team will do something, and the back-end team will say, it does work. We are trying to build enough of the care about the KPIs that you cannot violate early on. It's an approximation, but it's good enough approximation. The front part of the process is not created something that a fantasy that is not implementable. True, but verified. DVDs show they could use surrogate models to massively accelerate graphing rendering, said North. These are similar challenges that we faced with the sign-off. When you see this image, do you trust the image? All following physics-based principles, and I don't think we can rule out of role of AI and the calculations, but it does not display the importance of first principles. Physics-based algorithms are actually computing these things with the complementary. If they are surrogate models, where they are inferring the many pixels, they still require the calculation of seed to do that inference zone. AI also throughout the flow. In some software industry, AI is expected to create code. If a tribal knowledge in terms of designer expertise and a tool expertise can be documented, then you have the ability to learn from it, said Firubena Kadam. This is the power of LLMs. All we need is this knowledge to be captured in a way that can be ingested into LLMs. Since the LLM can do a lot of field work, you could ask models and generative application why the light long architecture of the topology for this particular spec. The LLM would provide recommendation for an architecture with an example and a whole bunch of other collateral that can help. Other people would like to see the AI help specification and requirement. The challenge is you have thousands of requirements and it will be hard to identify logical errors within them. Said Frouch. This task is typically language to logic or language to a mathematical representation, and this is the sweet spot of AI. The key that must talk to engineers when people ask for reasoning. What they usually mean is interpretability. Outputs that humans can verify, said Srinivasan. LLMs doesn't reason like humans. They do transformer decoding. But if you constrain them to output a plan with the steps, it looks like reasoning and it becomes workable for humans. That is now really reasoning. It is a constraint on how we display outputs of people can interact with them. The point is designing human AI collaboration, not making machines things like us. Rapid revolution. Given the pace of innovation as all kinds of AI, it is clear the industry can expect to see rapid improvement both within these EDA tools and in agentic AI tools that can help to relieve engineers from some of the burdensome tasks involving tool iteration, new technology, and new capabilities getting rich data every day. Said Gupta, we are constantly evaluating the opportunity to use these new technologies under the hood to be able to speed things up. It is unique. We need to move faster. At the pace that the industry is moving the foundational technology, we'll continue to see the pace of the AI capabilities coming into our tools keep growing. With it, the role of engineers will change. We expect AI that will enable teams to build a much larger number of chips, said Balanaga. We anticipate that the combination of advanced agents and improved tools will dramatically extend the design capabilities, and this will shift human effort to the meticulously defining the architecture specifications upfront. From there, I will handle most of some downstream tasks with a human acting as orchestrators and resolving any ambiguities in designer intent. Relatedly, the future of the formal verification, will formal verification be a part of the future, or will we continue to see a natural language specifications? Will formal successfully break out of just the functional verification? Brian Bailey. Okay, today I read this article. AI plays multiple roles within EDA. Thank you for your time. See you next time.